This week we're talking about cylinder heads. Now your cylinder head is probably the most important part of an entire engine build as far as the potential to make power. That's because our cylinder head is getting our air into and out of the cylinder. Out of the cylinder, not really that difficult. Usually we're not too worried about what the exhaust is doing because after combustion we've got a very high pressure in the cylinder, and any valve opening, it's moving a lot of air. We just want it to be efficient when it does it. So really the important part of the cylinder head is getting the air in, because that is the far more difficult process of it. And then once it's in there, we want to make sure it has a design where once the air and fuel have gotten into the cylinder, we're having a good complete combustion burn. Now to get the air in, there's a lot of different components that it has to get past. Now if we're gonna focus on, say, a typical pushrod V8 inline like a small block Chevy or Ford, on the way in, starting with the cylinder head, we've got the push rods to get past. Then it needs to navigate any head bolt holes. And then we finally get to the cylinder components where we're going to be able to get it in, but we've got the valve and guide, and then the seat and valve, head, before we get into the cylinder. This may not seem like a lot, but you have to keep in mind that air does not like to go around corners. So to really talk about cylinder heads, we've got to talk about air a little bit. And air is a fluid. Like, it's kind of a weird way to think about it, but yes, air is a gas, it's not a fluid, but it moves like a fluid. And it moves like a fluid because it has mass, especially after we add a fluid to it, which is our fuel. If we're talking about a carbureted V8, that's way upstream at the top of the intake manifold. If we're talking fuel injection, we're definitely closer to the head, but still in the intake manifold. The only way to really get around having the fuel in there is to be a direct inject setup, which comes with all its own kinds of ups and downs as far as doing an engine build. Really, the technology is in the aftermarket for doing a build is just getting warmed up as far as direct injection, mostly with like the LT GM market. But for the sake of the other 99.9, we're gonna talk about fuel being added to the air. Now, if we've got a tube and the air's just moving through it in a straight line, we're gonna have a lot of air flowing. And we're gonna be able to add fuel to that, and as long as it's atomized when it gets added, the fuel will be in here and all mixed up and great and happy and everything's good. But that's not how it's moving through our cylinder head. We've got all this stuff in the way. And most cases, we've got a cylinder head that at the bare minimum needs to make a corner. It may not be completely 90, but the air, because it has mass, wants to crash into the back wall. And the whole thing about me saying mass is, inertia. An object in motion wants to stay in motion. The same thing applies to air, even though it's so thin you can swing your arm through it and hardly feel it. But we're not talking about it as ambient when it's in an engine. When it's in an engine or flowing through an engine, because an engine is just a big air pump, it's moving very fast. And it's not just moving in one direction, because we've got a valve in here that's opening and closing. It's actually stopping flow and then letting it flow, and stopping flow and letting it flow. Well, all that air is moving and it hits the back of the valve and bounces off. So air isn't moving in a straight line through a tube as it goes through an engine. It's actually moving forward and then backwards a little bit, and then forward and then backwards a little bit, and then forward. So we have, basically, if you know electricity, direct current would be a straight line, but this back and forth that we're creating with the air pulses as air moves through an engine is more like AC current, because it's going in both directions. And we'll get into more of that in the technical side of it when we start talking about intake manifolds and some of the cylinder head porting classes and stuff like that. But it's something to bear in mind, that it's not just air going into an engine. There's like everything all the way back to your throttle blade matters about how this air acts as it's getting through your cylinder head. But it's a little bit off topic, but it's something to be aware of. Now in our example here, where we're turning the corner, we've got our fuel in here, but if this corner, aka the cylinder head, that's what's making it turn, is the shape of the cylinder head around here, isn't a good design, this fuel doesn't stay in suspension. And if it's way too fast, it'll actually just throw all the fuel against the backside and it'll puddle and turn back into a liquid instead of being atomized and just run to the cylinder. The same thing can happen if it's too slow and it just falls out and just dribbles down wherever. So we need to have a cylinder head design where everything stays as nice and atomized as possible to get it into our cylinder fully atomized and ready to burn. Now with all these things in the way, if we've got our push rod holes, a head bolt hole, and finally getting to our valve, and we need to have a port that gets through there, if we're looking at it from the top, you know, we've got a pinch point here at our push rod that then has to negotiate around a head bolt hole and be able to get a port that gets to our valve. This is where these things being in the way comes into play. Because now we're not only negotiating just a single turn from flange to cylinder, we're also adding several more turns depending on the cylinder head just to get the air to the valve, much less in the cylinder. And the more it turns, the less, I want to say, the quality of the air getting to the cylinder is lower when there's more turns. It's not that it's bad, it's just that it's not as good as it could be because of your fuel being in there along with the air, and every time it turns, that is just more opportunity for the fuel to fall out of suspension, or it slows down the air and it just doesn't end up being as good as it could be. You know, for an example with what I just drew right here, you know, if we had a port where, say, we didn't need to worry about this head bolt hole, let's say the head bolt holes were here and here, well, even if the push rod doesn't change, look how much straighter of a port we can suddenly make because that head bolt hole isn't there. Like the quality of air you're going to be able to get is going to be much higher, and it's going to, provided that the port that's actually in the cylinder head is of a good design, but that's kind of the point, is that cylinder head designs are all different. They come in all shapes, sizes, flavors, all kinds of whatever. And especially in say a typical small block Chevy application, there's such a gigantic range of styles of cylinder heads to choose from that depending on your power goals, this is the type of stuff to start looking at, because as you move from a OEM cylinder head or even an OEM based design cylinder head into all of the aftermarket options, all of those aftermarket options are working towards making this air and fuel getting to the cylinder better. That's how they're making more power. And the designs can get crazier and crazier and crazier as you go, all the way up until it's something that isn't even remotely recognizable as a factory head, just because it's been changed so much in order to improve the quality of air getting to the cylinder. Now take note that I keep saying the quality of the air getting to the cylinder. And that is because I'm not talking about raw airflow. Like the CFM that a head flows is not what we're talking about here. We're talking about the quality of the air. And that is referring to, we want the air to not be turbulent. We want to make sure our fuel is fully atomized, or as close to it as we can get. And we don't want the air like doing anything funky along the way inside of the cylinder head port or after it gets into the chamber. And we want nice, smooth, consistent airflow, which is high quality air. If it's tumbling and doing all kinds of funky things, that's not high quality air getting in. So I just want to make that distinction, that it is different. Now, if we're gonna compare some cylinder heads, like say you just got your catalog open, looking at cylinder heads, most of the time they're gonna list it by intake CC. And what that's referring to is the cubic centimeters of displacement that the intake port is in size. And this is really kind of a terrible way to compare cylinder heads unless they're all of the same design. Then it's a pretty decent way to tell the size of the cylinder head port. What I mean by that is, let's say we've got a 23-degree typical small block Chevy. Well, if we're looking at a 185, a 195, a 200, a 215, we can pretty much easily go with the idea that the 185 is a pretty small port. It'll be good for a smaller engine or building torque on a larger engine at lower RPM. And as we move up in port size, that port's going to get bigger, it's going to flow more air, but if we're not changing the size of our engine, the air is going to be flowing slower or have less pull on it because of the size of our engine. So if we're using our small port on a large engine, the engine's going to be making a bigger pull. That's going to have good high airspeed on a small port. It's going to make torque and it's going to make it at a lower RPM. If we've got a small engine with the big cylinder head, so the complete opposite, it's making a small pull, which is not going to make a lot of airspeed, especially on a big port, until it gets high up in the RPM range to start making enough pull or pumping forces, because the engine's an air pump, to move enough air to create good airspeed in the cylinder head. Now, this is important to understand because air has kind of a speed limit that it can get up against. It'll only go so fast, and then same thing with our atomized fuel being in there. There's a point where it's, you need it fast enough to keep the fuel atomized, but then going too fast can also make the fuel fall out of suspension, because now it's got so much speed that we're literally just throwing it against the port wall when we try to make it go around a corner. And there's a sweet spot in there where heads make great power, regardless of what they're on, provided they're designed properly around your engine build. They'll make good power almost everywhere, kind of a thing. And, it's hard to get. It's harder to get in say an off-the-shelf as-cast situation. You either gotta, have a ported cylinder head or something that's CNC'd, or just a head that's a really, really good design right off the bat in order to accomplish that. But that's why cylinder head porting exists, is to alter the shape to help the air flow through the head past all of our restrictions and around the corners it needs to make. Getting back to port size here though, as long as we're comparing 23-degree heads that are all for the same application, this is an okay comparison using the intake CC. Just out of generalization, these are probably going to be as cast sizes. Getting to a 215 might start to be a CNC'd port, where they started with the 185 head and then CNC'd it, and now the shape that they made is displacing 215 cc's. The bad part is now if we're going to get into trying to compare it to, say, an 18-degree small block Chevy head, because this degree difference is referring to the valve angle. So our cylinder is straight up and down. We got our valve coming in at an angle. So a typical small block Chevy, that is 23 degrees. Now you go to an aftermarket head of an 18, and now that valve's a little flatter, and now it's at an 18-degree angle. And there's even lower angle numbers than this. The reasoning for that is they're changing the angle of the head because they're trying to work with the combustion chamber size to make it smaller. And that's, you start getting into really high performance heads, kind of nothing other than your bolt holes and your push rods, and even the push rods are movable, is like everything's negotiable at that point as far as what is able to be moved around to improve a cylinder head. But with the port CCs here, probably, because we're, talking a high performance head here, this is probably going to start at, say, a 215 and have a 230 and maybe a 250, or whatever in port sizes. The actual numbers are not important for this discussion. But this 215 and that 215 are not equal to each other. Not even close. So you can't compare this 215cc head to this 215cc head in terms of, oh, they're going to be exactly the same. No, they will not be the same. They're not even going to be close, because this head probably has a whole lot more done to it with a
might have offset push rods. It probably has a smaller chamber. It most likely has a raised runner, which, you know, raising the runner, you know, if we're talking, we got our chamber and our valve coming off, and get our port drawn in here over to the intake flange. Now you might have a typical port that's going to be kind of some shape like that, but a raised runner port is going to be moving that intake runner opening at the intake flange up. And even if the valve angle doesn't change or anything else like that, you can see we've reduced the amount of turn in the cylinder head. So even if these two ports are the same size, the air quality being flowed through them is going to be different. And because this is up higher, it's automatically going to make our raised runner bigger. So really, you know, if we look at the cross section being, if you're looking at it from the intake flange, is the area of the inside of this port. You know, so if we got 1 by 2, we've got 2 square inches. I think that would be our cross section. And if our 2 ports are the same size, the cross section won't be the same between them, because some distance or volume needs to be taken up with this port being raised. So the cross section of that raised port is going to be smaller, and that's going to make the airspeed higher in it, which is actually going to act a little bit more like one of these smaller heads. So really the point here is that this is not an apples to apples comparison. You know, you can use it for a base level comparison as long as the cylinder head type is exactly the same. Now I could keep diving into the shape of the intake port and all that stuff, but I mean, really for 95% of you, it's not going to be an important thing, because you're going to have an engine and it's like, this is the type of cylinder head that we have to work with, and you're not going to be able to kind of go a la carte with the cylinder head and pick and choose every little detail about it. And a good example of that, like anybody building something for the street, you know, typically even on the small block Chevy side, you got all those race head options. Probably going to end up just picking a 23-degree head anyway, because there's a lot of really good options out there, and you don't need a full-on custom race head for a street application. We will be getting into more of the technical side of that stuff in some of the cylinder head porting videos that'll be coming up. I don't want to turn this into a 3-hour video. So once our air gets to our chamber, we've got several different ways that the chamber can be designed. Could just be a big open bowl. With a couple of valves in it. We could have something that just has a couple of flats. All the way to having our kidney bean or peanut shape in there where we've got material added in to try to make as small of a chamber as possible. And a lot of that is just going to be based around, you know, what fits, what works, and the chamber size that we're shooting for, because a smaller chamber, again, it's measured in cc's, so a small chamber is going to be higher compression, because as the piston comes up, you're squeezing that, you have a smaller space that all of that air is being squeezed into. And an open chamber is going to be lower compression. And really, the shape is less about performance and more about making the compression ratio you want for that engine, because you could buy for example, a 75 cc chamber, that's a fairly big one, or you could buy a 64 cc chamber, which would be making it smaller, making higher compression. And sometimes that's determined with the head. A lot of times it's also determined with the piston, because we'll use the cylinder head to make our airflow better in a performance application. Where that comes into play is when we start talking about how the air is coming out of our port and into our chamber. So if we've got our port, and then we're going to have our valve seat. And if we just have a really flat chamber, so this would be a typical small block Chevy where it's got a lot more chamber on one side. That's due to the valve angle, and like we were talking about earlier. So the more that this valve gets stood up, the smaller the space can be made over here. Now when you get into performance applications, you know, this air, like I said, it doesn't want to turn corners, so it's got to turn a lot to try to fill in these areas. And that can cause turbulence where the air starts coming in, and then it's so far that it kind of ends up being turbulent just to fill those areas, kind of a thing. Now in order to fix that, some cylinder heads will change the shape. Where we come off our seat, and then our chamber starts looking like that, where now we've eliminated all of this void over here, and the chamber is a lot smaller. So this would be getting into our peanut kidney bean shape. And now when our air comes into the cylinder, it is supported the whole way. So it can flow nice and smooth around the valve. Because yes, we still have our valve in here. So it's got to get around, and then same thing, the back of the valve is shaped in a way to support that air also, where it'll flow nice and smooth around each side. So with all of those things, we're improving the quality of the air. The other thing is, as we're transitioning from this super flat to this steeper edge along the valve, our valve angle, or valve seat angle, can get steeper. So 45 is the typical all-arounder valve seat angle. So that'd be the where it seats on this valve against the head. Now, when you got a super flat style chamber, typically a 30-degree seat might be better set up for that head. Some OEMs ran 30-degree intake seats back in the day, and the 30-degree seat makes more airflow at a lower valve lift because at the flatter angle for a given amount of valve lift, the space in between is greater. And I know that sounds weird because, like, well, if it's lifting 100 thou, it's lifting 100 thou. Yes, but it's if you're looking flat to flat and we lift 100 thou, we've got 100 thou of space. But if we're at 45 and we lift 100 thou, we've got 100 thou between here, but that doesn't mean we've got 100 thou between everything else, because we've got the port, the chamber, the valve, and everything else in the way, where those things the valve didn't just magically shrink 100 thou all the way around. It only went in a linear direction. So you can flow more air with a smaller seat angle at low valve lifts. The problem is by the time you hit a 1/4 inch or 300 lift, it stops being better. And a 45 will start to flow more air than the 30 at a higher valve lift because the angle is softer and it's making that air turn less. That being said, the farther we go with using our chamber to support our airflow, we start getting into where a 50-degree seat might be a good option, especially if we're talking high valve lifts. And I haven't personally used one, but I have seen seat cutters for a 55, and I think that's kind of about maxed out, because you also get to the point where if it's too steep, if it was 90 degrees, you're not sealing anything with the valve because it can't put any pressure on. So kind of this is an upper limit. It's definitely not very common to go past 50. But the 50 also gives up more at the lower lifts. So if we just had like a stock cam in something where we see 450 of valve lift, a 50-degree seat is not a good option for that, because it's only going to start trying to work probably above that. A 30-degree probably be pretty decent. It's just you're also, if you're talking a really bad port design where everything's really sharp corners and the air has to slow down a lot so that it can turn around all those corners. We're not really talking about a performance head at that point where that's a good option. Is that 45 is kind of the go-to all-arounder, because it doesn't give up a whole lot compared to the 30 at low lift, and it doesn't fall on its face at high lift like the 30 does. So a 45-degree seat angle is what almost every head's really going to come with, unless you're talking about a much higher end race style head. Now, much like the ports themselves, with the chamber, kind of sky's the limit. You can do a little bit of anything and everything if you're blank sheet on a head. Now, if we had our big open chamber, nothing in the way, and we needed to decrease our compression ratio with the cylinder head because we don't want to change our pistons that we already have, Well, you could have a cylinder head that adds a little material to the chamber down. So you move the valve, you could add to the deck side to make the chamber bigger. You could cut your valve job deeper, which is the easiest thing to modify as far as chamber size. So instead of our valve seat being here, we can cut it deeper into the head. That moves our valves down, adding cc to the chamber, because your valve height absolutely has a big effect on that. Or we go to a closed chamber style head, but if we're already talking a raised runner head, perhaps we need to meet the same compression ratio, so the entire thing got moved deeper into the head and the port went up with it, in which case now we've got a larger volume out here, even though we've got a closed chamber head with our tighter shape. You know, there's like everything can change a little bit. It can also, well, if we need to lower compression ratio, but we've got a closed chamber head with this real, you know, tight support area, well, we could come back and, you know, lay this chamber back a little bit more, just to add a little more cc if need be, and that can be done with just porting techniques and grinding on the cylinder head or getting it CNC'd to a different shape. You know, anything and everything can be changed here and adjusted, and it's just whether or not you want to get into that much nitty-gritty of it, or if you're buying an aftermarket head anyway, just pick the right one for the application. You know, and that's just, I can't tell you what's the right answer for that, because it's going to be a little bit different for every type of engine build. But if we're talking high performance engine build, which is why you're watching this video, we're gonna want to stay away from a big wide open chamber unless we have to for the compression ratio. We're gonna want to have more of a closed kidney bean shaped chamber if we can, and that'll get us that airflow support we're after for having either a 45 or maybe even a 50-degree valve seat angle, so that we know we have a good port, we've got a good chamber, it's just a good cylinder head all around to make higher compression, large cams, big intakes all work together. For the nitrous guys, there's something that, if needed, can be done, and that is chamber softening, where we actually turn it into an open chamber, but we're not doing it like this. We're keeping a lot of our shape, but then we'll lay this edge back on both sides, and that's just to eliminate the sharp corner on each end where our chamber meets the deck, because all of this otherwise should be flat area. And it's flat because where the flats meet up with our piston when it comes up is called quench. And we're running, when the engine is running, that becomes a very, very small gap. And the idea here is that we're making it so small that the air and fuel has to be thrown back into the center because we're pinching it so tight. Well, in a nitrous application, depending on, you know, what air and fuel gets stuck in there, it can make a detonation area if we got a sharp corner. So in some applications where that's needed, we end up doing this chamber softening so that there are no sharp corners, and it all just more can get funneled back into the middle, but then we lose the quench area quench area is really just trying to take that portion of the cylinder and throw everything back in and kind of pretend it's not there, making it seem like the whole thing is just a little bit smaller. There's plenty of discussion and argument about whether you even need it, what size it should be. It's honestly, for the average person, you don't really need to worry about it. Just as long as you're not too tight of a gap where you're having contact between the piston and the head. And once it's, past a certain point, you kind of, in size of that gap, it just loses it's a little bit of a benefit. You're not really hurting anything. So really you shouldn't be too worried about any of that, and I've never done any dyno testing where we can go back to back testing the importance and the power production of quench. Just, it's something to know, and most cylinder heads are going to be designed with some type of quench as a factor between the piston and the head, just because they're making the shape to work with the airflow and just leaving everything else flat. Now, I feel like we do need to touch on a Hemi, and I mean a proper old school Hemi, not a newer semi-Hemi. The combustion chamber is legitimately almost a complete upside down bowl shape in a Hemi. The benefit of which is I can put really big valves in them. Because they, instead of being limited to just the shape of the circle, they've tipped it back and created enough space to put this very large valve in. It also has a secondary benefit of the ports become very straight. So, old school Hemis flow huge amounts of air. That's why they're on all the top fuel dragsters with big blowers, because those guys are at the point in engine billet where as much as you can cram in, it'll take. The downside is you can't make a good compression ratio without having a dome piston. And like we talked about the short block class, a dish piston will make more power than a dome piston, all things the same. And it's just not an option with an old school Hemi, because you'll just never get enough compression ratio out of it because the chamber's just massive. The other part is when you look at the way everything's arranged, you start talking about a very wide head, very big rocker arm system to get everything to work. There's a lot of just requirements that go along with the design that make it expensive as well. If you ever looked at the price of Hemi parts, valve train parts compared to a regular old inline V8, like the rocker arm system is at least 4 times, no, it's got to be more than that, 7-8 times more expensive for rockers, just because of the sheer size of everything. It's just so much bigger. Now I bring up the Hemi in this situation because of this super nice port shape. So if you're thinking ahead a little bit, like, well, why don't we just take that port and put it on our inline head? And yeah, that's a great idea, because now we are changing our port into something like that. However, as you can see, we are now way, way higher where our intake manifold begins than we were. So if we're talking about anything that needs hood clearance, it's kind of a, nah, I can't do it. I will say the flip side to this is going to be the newer GM LT series. They've got really tall, straight runners. You know, but if you look at that cylinder head compared to an old small block Chevy, they're huge. It's a huge cylinder head compared to a 23-degree small block Chevy head. Like it is so far different, but it's also very much a high performance, almost race quality level head from the factory right out of the box kind of a thing. But it also comes into hood clearances issues, so the intake manifold's got to be a lot different. From what I've seen, you know, a lot of the LT stuff there, you know, we're working with superchargers. So the supercharger can be stuck down in there. You can compromise a ton on the intake manifold itself just because you've got a supercharger, you're making boost, and you can compromise because you're forcing the air in, that it can be kind of garbage everywhere past here, and as long as this part is pretty good, it'll fix a lot of the air on the way into the cylinder, and it still makes power. But we're talking compromises again. So how do you choose the right cylinder head for your build? Well, this is one of the things where there's no right answer for everyone kind of a thing, but we can make some generalizations to help us narrow down the window to maybe pick from a few different ones. What's going to play in is engine displacement. This is going to be the big one because the bigger the engine, the bigger the cylinder head you can run and still have it work good in a certain RPM range, which leads us to RPM. That being, are we building a race engine that's going to turn 7,500, 8,000 RPM? Or are we building a street engine that's going to turn 6? Are we trying to build a tow rig engine and we don't care what it does above 5,000? That's going to play a big factor because the race engine versus the tow rig engine are going to be wildly different cylinder head choices. And another is our cam. And really the cam and the head should kind of be, I don't know, it's kind of like the, which one do you put first? And I would say we're probably picking the cylinder head based on our engine displacement and RPM goals, and then we'll pick a cam to go with it, but we can't just pick a cylinder head without thinking about our cam as well. Simply because our camshaft might have lift requirements, like say if we've got if we're going for big RPM, there's a lot of different style of cylinder heads that can get us there. But if we're needing to have a say 800 lift cam to do it, we're going to need a cylinder head that can actually do 800 worth of lift. Versus if we're doing a street engine and we're going to keep our lift under 600, so that's got longevity. Most any cylinder head can be made to handle 600 lift, and we don't have to worry about picking a special head because of the cam requirements. Now when it comes to the engine displacement, we're smaller to larger. That's kind of going to be in line with the port sizing of our cylinder head. I say port sizing because it doesn't matter the actual physical cylinder head size or design. It's going to come down to port sizing. And like we touched on earlier, smaller engine displacement has less of a pull. Bigger engine's going to have a bigger pull. So a bigger pull can make use of a larger cylinder head port and get the airspeed into the window where it's good at making power. That gets us to our RPM. So a low to high RPM, kind of the same thing. The lower the RPM range, the smaller the cylinder head where port size we're going to want to work with. The higher the RPM, we can use a larger port, but if we have a small engine and high RPM, we still don't want to go with a giant port because we're probably never going to actually reach the RPM where we'll get our small engine to make enough airflow, or to make enough airflow to get the airspeed into the good window in the cylinder head. And that goes along with our cam, a small cam to a large cam. This gets a little bit messy because, as we covered in our camshaft video, area under the curve. We make more area under the curve. You would think that we're moving more air the larger the cam is, and that is true so long as these two are also working in favor of moving air. Because a large cam is going to have a large amount of overlap, and even if we've got a large displacement but at a low RPM, if we've got a large cam and it's got too much overlap, it just dirties up everything. It's going to run like garbage. Even though we're using two things that are benefiting us, that through a large displacement, low RPM, we pick a small cylinder head, you put too big of a cam in it and you're still dirtying everything up and it's not going to work well. But if we picked something in the middle, it might actually work quite well with a large displacement engine at low RPM because we're putting a cam in it that will do a really good job filling the cylinders at our target RPM range. Now, a smaller engine at low RPM, we kind of got to stick with a small cam because we're just not going to be able to use our engine displacement to get away with making our cam bigger. And just to re-explain that from the other video, a larger engine will make a cam act smaller, and a smaller engine will make a cam act bigger. So this is kind of a moving scale based upon engine displacement, and our RPM range is just kind of where we're going to then add a second sliding scale to our cam choice. And I realize this may all seem confusing because these are just big, broad generalizations, but if we really want to get down to, what is most engine builds actually going to look like, typically you're going to be working with what you have, especially if you're not doing a small block Chevy or LS where sky's the limit on options. Now, as an example, on the very stockish side would be one of my Oldsmobiles, for example, if I'm building a street engine for an Oldsmobile and I've got a power goal in the 400 horsepower range, like I don't even have to think about it. I can either do out of the box Edelbrocks and bolt them on, and I'll make that power. Be totally fine, ready to go. But it's going to tell me that I need to pick a cam to work with the out-of-the-box parts unless I'm going to go change all that stuff. Or I can very much get to that power level with the factory heads. I'm going to want to get them ported so that we're improving our port shape and getting more airflow in there, but it'll still make more than enough airflow to make that power level. And the ports are going to be a little bit smaller on the factory head than they are going to be on the aftermarket head. And I could get away with a little more camshaft, potentially, to cheat that power up a little bit, even though I don't necessarily have the cylinder head to go to a high RPM, but because I'm building a street engine, and I'm okay with a lower RPM setup, I can put a little more cam at it, and even though the cam is going to be limited by the cylinder head, that we won't be able to make more RPM, we'll still be able to add some airflow and build more power in the mid-range kind of a thing. Flip side of that would be, say we're building a small block Chevy, like we've got any cylinder head possible to think of that we can choose from. Really, it's going to kind of come down to goals and budget, just like we talked about in the very first introductory class video, where, you know, if you want to make 500 horsepower, well, you can do that with a 23 degree head. You could do that with an 18 degree head. You can do it with a 14 degree head. You could do it with a bore rotated splayed valve race head. You could do it with, I mean, anything is capable of it at that point. But the 23 degree head is the budget option, and there's a ton of options even within that category, where then you come down to, okay, you need to, all right, what engine size are we going to do that with? Because 500 horse is pretty easy to do. We could do that with a 327. We could do it with a 427. 427 will obviously do it much easier because of the additional displacement, and it will do it with, you know, I don't know. Honestly, they probably could do it easily with the same cylinder head. It's just the 427 is going to be making significantly more power. I mean, they'll both get to 500, but the 427 will do it at a lower RPM with that same cylinder head. And even they could even probably have the same camshaft at that point in time. It's just because our cam is going to act bigger on the smaller engine and it's going to act smaller on the larger engine. But between the cylinder head and the cam, airflow wise, we're getting to that point where we can make that power, and the engine displacement at that point is just deciding at what RPM we're doing it. So this is the part where, I mean, just like everything interacts with everything else. And you just need to kind of be aware of it. But at the same time, most of you aren't going to be blank sheeting an engine build. You're going to be working with something you already have, you know, or you've got a power goal in mind, and there's plenty of different ways to get there. I mean, honestly, just to kind of be silly about this, like say we only needed to make 200 horse. Well, a smog era big block Chevy can make 200 horse, and it's wheezing to do it. And you can also have a mildly modified Honda K-Series and it'll make 200 horse, no problem. And it's running really great. to make that. So like there's all kinds of extremes and in-betweens, but all of this is adding up to what do we want it to do at the end of the day, like we talked about in our very first video. Like what are the mannerisms of the engine, or the personality of the engine that we want going to be out of it? Because if we're wanting a cruiser that makes lots of mid-range and drives really nice, but we've got our smaller engine and we don't have the big displacement to lean on or use as kind of a cheat code, then we need to make sure that we're not picking a giant cylinder head to go with it. That's only going to start making power on that little engine at a high RPM, because that's not where we're actually wanting to use the engine. So we're going to need to pick on the smaller side of cylinder head to go with our smaller engine. And if we've got those two things lined up pretty well, we can actually cheat up our power a little bit by putting a larger cam in it, because we're getting that cylinder head into our airspeed range for our smaller engine in the RPM window we want. And then therefore we can use our cam to cheat up the amount of air getting into the engine and make a little more mid-range and top-end power, even though we've kind of compromised a little bit. But we didn't compromise, because we picked things that worked together, and therefore the engine will perform in a way that's kind of a little bit above and beyond, or hitting a little bit above its weight class, just because we're making all the parts work together. Once again, we're going to dive way more into the nitty-gritty of cylinder heads when we get into the porting videos. I don't want this to be a 4 or 5 hour video, because there's going to be so much discussion on the little nitty-gritty bits of a cylinder head, and I wanted this to be more of a generalization for cylinder heads and choosing them, because we're going to get into intake manifolds and headers. And I think at the end of that video, we're going to kind of tie everything back in, because your induction system, which would be everything from the throttle body or throttle blade in the carburetor to the cylinder, is your induction side. And then we've got the exhaust side, which is going to be everything from the cylinder out the tailpipe, so to speak. And your camshaft, again, plays into this as well. But all of those things need to work together to build a really great engine. If you mismatch components anywhere along the way there, you can screw them up badly enough with mismatch that the engine will not perform well at all. But you can also get them pretty easily into a window where they're all going to kind of work together, and it'll make a really good engine. And then if you really science it out and you're going for a specific use case, you can actually pick components where they work together so well that it just like really outdoes itself compared to what you might look like it should be doing. And that's really cool. I like getting into that stuff, but we need to move past just the cylinder head. We got to talk about those other components first to really discuss how to make all that stuff work together. So, upcoming videos for that.